me. See, I'll be talking on the availability assessment of Markov repairable system with an uncertain inspection period incorporating Q. See, basically, I'll be going through some of the basic definitions of the reliability studies so that the other researchers, young researchers who are basically not of this field can also understand what are the things which are basics to the reliability theory and how they can start if they are interested in working on in this field. Yeah, basically my talk will be focused on this reliability. What is reliability? What are the expectations of from the reliability experts and how that can be achieved? What is the repairable systems and how inspections can play a role in maintaining the reliability of the system, and what we mean by system maintenance, availability, and next, importance of the queuing theory in improving the system's performance, and lastly, some theorems will be derived for the considered system, and conclusion and references. See, I'm just going through the overview of some of the basic definitions, as the time is also not very very good. I mean to say that it's slightly 30 minutes time is given. That's why it is not proper to define all the things in a very elaborate way. Anyway, reliability basically means the probability that the system will operate successfully under the given circumstances. I mean, given circumstances means under given time and whatever the environmental conditions are there. See, that can be expressed mathematically as RT, or probability capital T. Capital T is the time of the system failure is greater than small t. If that's the case, then it means the system is not failed, and that is basically expressed as the reliability. If in terms of the failure rate, then it is 1 minus ft if t is greater than 0 and 1. Yeah. Then what are the expectations from reliability experts? See, basically, the industries who wish to design the product in such a way that it is failure free, but it is next to impossible to design a product which is never going to fail. But there are cases where it is required, but more often it is not being achieved. Now, if the failures are there, then the second task is, if the failures are there, then how easily, how fast it is diagnosed, and once it is diagnosed, then how the rectification actions are being taken, second. And thirdly, now the expectations from the reliability experts are that what are now several modern techniques are available, how those modern techniques are being incorporated in the designing state so that the reliability of the product is improved. See, what we can achieve out of doing all this. See, one, reputation of the product, and of course, if the product reputation of the product is improved, then the company which is involved in producing that product will also going to improve. Secondly, the customer will be satisfied. If the customer is satisfied, then definitely the sales of the product may be improving. And thirdly, and the very important thing is that more often when we go to the market to purchase some of the systems, some of the products, any item, then we wish to check whether some warranty or guarantees are being given or not. If some warranty or guarantee are given, then we more often influence towards that. But the thing, the opposite situation the company may face is that, say, warranty or guarantee is given, but during that period, if the more number of failures are being noticed, then company has to repair or replace depending upon the guarantee and warranty, and doing so a good amount of replacement cost is to be utilized, and in that way not only it is going to attract the negative attention, but it is also going to affect the product. Hence, warranty, if once warranty or guarantees are being given, actually before giving all this, the reliability testing are being made. But even though sometime it may happen that during that period more failures are being noticed. If that happens, then definitely it will not be not good for the company. And lastly, the customer's requirement are also nowadays that what other actions or are being actions, I mean what others features are being provided as far as reliability is concerned, or during related to reliability contest. See, as I said earlier, the, the failures in the system are not uncommon. But if the failures are there, then definitely we'll be going for the repairs. And if you are going for the repairs, then there are two type of distributions as far as analysis are concerned. We have to go for, one is the failure distribution, and another one is the repair distribution. And this failure distribution and the repair distribution actually depends upon the product dealing with, and accordingly those distributions can be decided or can be taken from. As far as performance measures are concerned, reliability, availability, they all are the performance measures. But whether we are going for the reliability or going for the availability, this all also depends upon failure and repair distributions. The failures can be classified like critical failures, non-critical failures, degraded failures, incipient failures. Critical failures are those failures where system is there in the complete breakdown. Non-critical failures are those failures where the performance is lowered, but it is not completely failed. Degraded failures are those failures where the system is performing but with degraded rate. And incipient failures are those failures where actually some failures are there, but it is not in the notice, and in the future that may lead to the more dangerous situation. See, as far as maintenance is concerned, see, in the study of reliability, of course, availability is the special case of reliability. The maintenance section is one of the very important action, and once the maintenance section is proper, then the overall reliability, availability, and downtime and cost of operation and many more can be settled or may be tackled easily. Hence, one has to be there as far as maintenance of the system is concerned. The company has to decide when to go for the maintenance, when we expect that the maintenance section is expected. Accordingly, they may decide. See, types of the maintenance may be classified as preventive maintenance, corrective maintenance, and inspection. Preventive maintenance are those maintenance where the actual system has not failed, but the we see that some action may be taken so that if any failure may going to happen in the future, that can be tackled prior to happening that failure. The corrective maintenance section is that maintenance where basically if any failure is noticed or failure is already happened, that is being corrected. And thirdly, in my talk also I'll be focusing more on the inspection. Yes, inspections are, I'm skipping this slide for the sake of the time. Yes, inspection. Basically, inspections are done to uncover the hidden failures or dormant failures. And by doing so, many times the failures which is not actually being noticed or which may occur in the future can be tackled during the inspection. The problem is that a particular type of inspection is not applicable to every system. There are different type of systems and different type of inspections are required. As we can say, the continuous monitoring is one a type of inspection, periodic inspection, non-periodic inspection. The continuous monitoring is those type of inspection where the continuous monitoring is required. For example, satellites are there, continuous monitoring is required. Periodic inspections are those inspections where you can inspect in some period, calendar period. Non-periodic are there where you may randomly inspect. These are the different inspections type, and they are applicable depending upon the system you are dealing with. See, Maintenance downtime is that time where the system is down due to maintenance action. And system maintainability. Maintainability is basically defined mathematically here as the probability that that system, if it is under failure, can be repaired. What is the probability that the system will be repaired or bring back to the operational state under the given condition, under the given time? That is known as the maintainability of the, yes. Now, availability. See, reliability already defined, and availability is defined as the probability that the system is operating properly when it is required to be used. Say, when you are interested in operating some system, and suppose you are interested in operating your laptop, and when once you are starting, if it is not functioning at that moment, it means your system is not available. Okay, in this sense, the availability is being defined. What is the probability that the system is found operable when you are interested in doing so? See, reliability as defined is the probability that the system is operating successfully, and the maintainability is the probability that the item is bring back to its original state. And reliability, availability, maintainability. These are the three key features in the study of reliability or reliability engineering. They are in short also known as RAM. Reliability, availability, and maintainability. See, if we see all these three key factors, then if the reliability of any system is constant and maintainability is decreasing or decreases, then the availability will decrease. If the reliability is constant, maintainability increases, then the availability will also increase. If the reliability is increasing and the maintainability is constant, then also the availability will increase. If the reliability decreases, maintainability constant, then the availability of the system will also decrease. See, availability can be classified like instantaneous availability, or that is also known as point availability, limiting average availability or mean availability, steady state or long run availability, inherent availability or operational availability. See, basically, what actually I mean or we mean by instantaneous availability. Instantaneous availability is the probability that the system will be operational at any instant of time t, any instant time t. This can be expressed with the help of binary variables, say sigma t, where sigma t is equal to 0 in case there is a failure in the system at any time t. If there is no failure, I mean otherwise, then the value of sigma t is 1. This is how this can be expressed, and this can be utilized during the discussion of availability. See, with the help of this binary variable, availability can be described as probability that sigma t is equal to 1. It is available, and that is as good as availability of the system. See, limiting average availability, where average is being taken. Long run availability is that where the when limit t tends to infinity in the instantaneous availability, then we'll get the long run availability. Inherent availability is that availability where we have got the ratio of mean time between failure to mean time between failure plus mean time to repair. This ratio is known as inherent availability, and operational availability is the uptime of the system plus ratio of uptime to uptime plus downtime is known as operational availability of the system. Yeah. How about Q can play its important role here in the study of reliability? See, more often in the research papers dealing with the reliability, we see that whenever there is a failure, the failure is being repaired instantaneously. But in the real life, it may be the case that the repair is being done instantaneously, or sometime it may not be. If it is not, then there may be some queue. If queue is there, then what type of queue is there? Okay. Yes, incorporating this also, we may derive some properties, some expressions, how the queuing theory or queuing models going to play its importance role in the study of reliability, of course, the availability. See, as you people may be aware that there are different type of queuing models, and depending upon the situation, those models can be incorporated, and incorporating that one, different reliability models can be developed here. Yeah. See, availability assessment of Markov repairable system with an uncertain inspection period incorporating Q. Let me derive some expressions. When we are interested in deriving the availability of Markov repairable system with an uncertain inspection period. See, the inspection period is not uncertain, and we are incorporating Q also. See, in this model, we are going to incorporate MMS in Infinity FCS Q model, and the system considered is a computing this system, and with the help of this expression, rather we're going to derive some theorem for this one. With the help of that theorem, what will be the upper and lower bounds of the long run availability under the critical repair time? Critical repair time here taken is that time where a time is being fixed. If the system is repaired under that time, then it is said to be yes, it is operable. If the repairing goes beyond that time t, then we have to go for the replacement. And the time t so fixed is designated as critical repair time. Just to clarify the model, some numerical values will be taken in last. Yeah. See, what are the assumptions or the fundamentals taken in this derivation? First, let us suppose that the inspections are performed in the interval tau n. But as said, the inspection period is not fixed; it is not certain. And to incorporate that one, what is being decided? Let the first inspection is tau n, and we are inspecting at the interval of tau n, but whenever we feel that in some, or whenever we find some failure in the inspection, then we are going to reduce the inspection period next afterwards, and next time again we'll continue with that period, but whenever we find the failure, then again we are going to reduce the inspection period. This is what we'll be incorporating here in this theorem, in the theorem which we are going to derive in the future. Future means just after these slides. And the critical repair time t, as I said earlier, defined. Yes. See, if there is a failure, it means there is some fault, and to deal with the fault, a random time phi is being taken, and the distribution function corresponding to that is f phi x is being taken, and the q, as said earlier, MMS infinity FCS Q model is being considered with working vacation. Working vacation means the repairman is not 100% available always, but he is in vacation, but whenever he is being called for, he will be available to repair the system. Yeah, see here, just a demonstration of what I have said earlier. See, tau 1 is the period, inspection period earlier. No failure is being detected in there. Second time, again tau 1 is the period, but a failure is being detected here. And t is the critical time. But the failure is it is being repaired before that one. That's why we will not be going for the replacement. Now, see, in this interval tau 1, we have noticed a failure. That's why next time the period is being reduced to tau 2. Inspected, no failure has been detected, but next time we are detecting failure, and it is being again under the time is under the critical time. That's why it is going to be repaired. It is as good as operational. System is as good as operational, means it can be operated. And next time again, because failures has been detected, it is the failure is being the inspection period is being reduced, and this is how it will be continued. See, with this, the theorem says the proposed system, the considered system for the considered instantaneous availability AT at any instant t, incorporating this MMS infinity FCS Q, is expressed as this: AT is equal to RT plus I summation from I to the ceiling function Ri minus 1 tau n minus Ri tau n into 0 to t minus iota tau n availability of t minus iota It's not iota, sorry, it is I tau n minus y d f phi y. Okay, I represents here basically the interval. Okay, say first interval, first I1, second I2, I3, I4, likewise I can have any value. See, as said earlier, tau n is the respective inspection period, phi is the system's repair time, and this f phi y is the probability distribution. For this, if this model, this queuing model is incorporated and the inspection period is taken to be uncertain, then the availability of the system will be this much. Yeah, to prove this one, say, let us define the stochastic process epsilon ts 1 when the system is working and 0 when it is not, means otherwise. Availability of the system will be probability that epsilon t is equal to 1 when it means system is available, it is operational. This may be classified into, or this may be decomposed into two parts: when the epsilon is less than t, when epsilon is greater than t. The sum of this may be decomposed in this form: for less than t, for greater than t. Now, when it is greater than t, if epsilon is greater than t, if it means the system's lifetime is greater than t, it means this is as good as the reliability of the system. And as far as inspections are concerned, as said earlier, epsilon is the system's lifetime. Then system's lifetime must lie between I minus 1 tau n and I tau n. Okay. I minus 1 is 1 less and next one. Okay. Previous, in between the previous and next, this epsilon and the system lifetime must exist. Incorporating this or including this, the probability mass function can be obtained as pi is equal to pi, which is p, capital I is equal to I, which may be, this may be said to be as good as this, which may equivalently be expressed like this with the help of the reliability. Now, considering the inspection interval which we have said earlier, then the epsilon t is 1 when epsilon is less than t. This can be expressed like this: p is means probability epsilon t1, I is equal to I, capital I is equal to small I, and probability epsilon I is equal to 1, such that t upon 2. This is a silly function because the inspection will definitely be some integral value tau n, which is less than epsilon is less than t. This may further be expressed like this, where epsilon is this much plus the reliability. In terms of reliability, the value can, as seen in the previous slide, this may be expressed like this. Yeah, after system failure, of course, we will be going for the repair with the random time phi, incorporating that probability of epsilon 1 when I is equal to 1 can be this y, and y plus delta y is the repair time. Here the repairing action is being performed. This phi is the system, phi is the repair time, and this phi lies between this phi plus and this is the probability distribution. Yeah, including the statistical properties and the mathematical concept. This may further be expressed like this, which may further finally be this is equal to 1 may be expressed with the help of availability of the system. Yeah, this and this equation 4. Equation for this equation 4 can be attained by equation 5 as this, which may be expressed like this as seen in the previous slide. Now, the system's instantaneous availability with the help of all these equations, I mean 3, 4, and 6 equations, putting down in that equation, we can get the value of availability of the system like RT plus this into integral 0 to t minus I tau n A of t minus I tau n minus y d. Yes, long run availability of availability of the system can be expressed as following the same thing what we have what I have said earlier. Okay, the inspection period is not deterministic; it is changing continuously, and in incorporating these queuing models, the long run availability, limiting availability of the system can be expressed or can be found to be this much, where gx is this, gx is basically this plus exponential minus mu x, lambda and mu here. Lambda and mu are failures and repair rate of the system, and ws, this ws is basically obtained because of the incorporation of this queuing model, and this ws is waiting plus service time of the system. Yeah, see the renewal, the help of renewal theorem, the availability, this long run availability, expectation of expected uptime plus expected downtime, which is, see, up and downtime, combination of up and down times makes one complete cycle, which may be said to be one cycle. Now again, expectation of uptime is expectation of C epsilon is the system's lifetime plus 0 to t p I tau n minus epsilon plus phi is greater than x tx, greater than x is the random variable used for the failure, and with the help of again the statistical properties and the queuing models, this may further be expressed like this, which can be simplified to this. See, expected length of the renewal cycle. Renewal R is the renewal. Okay, renewal. I again repeat. Down plus up gives the combination of down plus up gives the, say, expectation of I tau n plus expectation of the system's repeat time. This will give you the total expected length of the renewal cycle, which is as good as expectation up plus expectation of renewal cycle. Putting down the values so obtained here, we can get the value of A. See, the lower and upper bounds of the long run availability can be obtained like this. This is the lower bound and this is the upper bound. Just to express this one, if we take the value of the repair rate to be 1, if we consider the exponential distribution and the repair rate 1, and let 0.1 be the failure rate of the system, and capital T is taken to be 1, and tau 1, the interval of inspection, first inspection is 3, and then that is reduced to 2.5. Putting down the value in the expression, then the instantaneous availability is obtained like this, and the lower and upper bounds, upper bound of the long run availability is obtained like this, and lower bound is like this. See, this is already expressed that what I have decided and what is being discussed here. For the sake of the time, because time is, I don't have much time, that's why I'm not repeating the same. These are some of the references. Finally, I would also acknowledge to this work is being taken from one of my PhD advisors, Amisha Khati, and I also like to acknowledge her for this.